looking at checksums as part of our look at user input validation. And so we came up with a made-up checksum where we decided that we would use the last digit of a phone number to give us some sort of indication as to whether or not the phone number was made up. But like I said, that was a very simple checksum, and they're usually not nearly so simple as that. So what we're going to do today is we're going to look at a whole bunch of them, and then if we get time, we'll think a little bit about how we might program them up as well. In terms of working on these in the labs, you'd be looking at writing a function that takes a string and then comes back with true or false, depending on whether the thing looks legit or not. And recall last week I was saying the structure of that, generally the way to go is you assume the thing to be okay, you test it and with a bunch of tests, and if any one of those tests fails, then you knock it down and you just make sure in the code that you never pick it back up again. So it's okay until it's shot down, and when it's shot down, it stays dead. Okay, so you may have a bunch of different tests. The most common one you'll see, although you might not be used to it because you probably enter your wow, that's some rain. No. So I thought it was going to be too hot when you sat into your car, yeah? Okay, no. Come on now, guys, chill. So, the thing you'll most likely see, the thing you see the most of is credit card checksum. So, credit card numbers, most of them are 16 digits, and the last digit is a check digit or checksum. So they need to add up in a certain way, and if they don't add up, that tells you something is wrong. And of course, just because someone puts in a number that looks good, it doesn't mean that they have actually any money in their account or anything, but you can check if a number is just totally made up at random. Okay? And this is called the Luhn, or Luhn, I'm not sure, formula for credit cards. So this was a German guy, or man of German origin, I think, working for IBM in the US. And so basically what we do is, in general, the last digit is the check digit, and very often you're doing multiplying and stuff to the other digits. You never actually multiply the check digit itself. So if ever you can't remember what way it works, the check digit itself usually stays unaltered. So every second digit gets multiplied by 2 in the credit card. Then you add all the resulting digits together. So like if you get 8 plus 8 gives you 16, okay? 8 times 2 is 16. That's 16. You have 1 plus 6. So I will give you 7. So that becomes 7, for example. I'll show you now in a second. I'll show you now, okay? So this here up top is a credit card number, allegedly. And you take every second digit and you multiply it by 2. The ones then that get multiplied by 2, you add the digits together. So 9 and 9 gave us 18. And 1 plus 8 is 9. So that becomes 9 there. If you look at 8 there, 8 times 2 is 16. And 1 and 6 gives you 7. And there 7 times 2 is 14, and 1 and 4 will give you 5. So you get all these values, you add them all up, and it should be evenly divisible by 10. So in a minute, if we get time at the end of my talking, you can whip out your many credit cards and have a look and see how that works. So this is great for checking the most common error that people would make with credit cards, is that they transpose digits. So someone might say 44992238 instead of 83, and it catches that, for example. If you're good at probability, you could work out the odds that a totally made up number would be okay. We're not going to bother though. So this is the classic checksum, really. It's been around for a long, long time, and we use it in credit card numbers to this day. You can see why it's beloved of programming lecturers the world over. Because, of course, to implement this, you're going to have to loop through the digits one by one, but then you're only going to do something every second time. You're going to have a running total. You also have some jiggery pokery there to go from 9 to 18 to 1 plus 9 to 9. And at the end you have a mod just to sum it all up. You can see why programming lecturers love to set this kind of thing as an assignment or as an exercise. It's got it all. You've got your loops and your ifs and your mods. From a programming point of view, it turns out that adding digits together is really a pain in the arse. If you have a number like 18, for example, to get 1 out of that, you could do a div 10, which would give you the 1, and then you could do a mod 10, which would give you the 8, and then you can add the two of them together. But as it turns out, for what we're doing here, you can just subtract 9 and it's as good. So if a number is greater than 9 and less than 19, if you subtract 9 from it, that's the same as adding the digits together, I think. So 18 minus 9 is 9. 16 minus 9 is 7. 14 minus 9 is 5. So that's handy there. But again, you could see you'd have an if statement to do that or whatever. Okay, so that's the Luhn algorithm for credit cards. You can also tell something about the kind of card based on the number. So Visa cards start with a 4. I have never seen a 13-digit Visa number, but maybe they exist. American Express is a 34 or 37. MasterCards go from 51, 52, 53, 54, and 55. So I have seen, and it's really clever when it works, a situation, or sometimes they ask you what kind of card you have. I've seen places where they just ask you for the number, and then when the number is right, up comes like Visa logo or MasterCard logo or American Express logo, and you're like, wow, how did they know? But it's because based on the number. And obviously, if you're saying you're having a Visa card and then it starts with 5, well, duh, there's something wrong there straight away. Okay. So that can be useful if you really want to push the boat out. You can, visualize what the card should be. The EAN used to be the European article number, which is basically a barcode for products in Europe. It's now been adopted globally, so now it's called the International Article Number, although we still abbreviate it to EAN. I see a trivia question there in some game show. The last digit here is also a check digit. You can actually tell quite a lot from the number. The first couple of digits tell you the country in which the manufacturer is registered, which is not quite the same as the country of manufacture, but it's close enough. And the next couple of digits would tell you the name of the manufacturer. And then some more after that then would tell you the actual product. So you could tell from the barcode, this is an Irish barcode, something manufactured by whoever. Okay? So you can tell a lot from it. We're only interested there in the check digit at the end. So to calculate the EAN, you can see it's inspired by the Luhn algorithm, but here you multiply every second digit by 3. So some get multiplied by 1. So like the first one gets multiplied by 1, the next one gets multiplied by 3, the next one gets multiplied by 1, the next one gets multiplied by 3, the next one gets multiplied by 1, the next one gets multiplied by 3. Like I mentioned, the check digit itself there, the last one there, the 7 at the end in red, the check digit itself never gets multiplied. So if you're not sure how, if you can't remember which way it works, you know, do I start from the back, start from the front, whatever, just remember the check digit itself never gets multiplied by anything. It's always just a 1. In this case though, you don't have to do any jiggery pokery. You just add them all up and it's evenly divisible by 10. Yip-de-doo, you're sorted. So you could take out, for example, there now, a can of Coke or a packet of crisps or anything, and you could multiply up the numbers. Or your coffee cup there, does it have a barcode on it? No. Okay. Anyway, anything that has this kind of barcode, you can look at that and you can tell, you can do the maths and see that it should come out evenly divisible by 10. Again, you can see why programming lecturers love this. You've got your loops, you've got your if, you've got your mod, got the whole lot. The ISBN number is a number that's assigned to a book. So each book has a unique number. So if you want to buy a book, actually all you need is the number. And away you go. There are two forms of ISBN number. There's ye olde ISBN, which looked like this. And this was much trickier to program because the first digit was multiplied by 10, the next digit was multiplied by 9, then the next one was multiplied by 8, and the next one was multiplied by 7, and then by 6, by 5, by 4, by 3, and by 2, and by 1. And once again, the check digit at the end was the one that got multiplied by 1. You multiply them all up, add them all up, and then you do a mod 11, not mod 10, mod 11. And if that comes out at 0, if it's evenly divisible by 11, you're sorted. So this meant, for example, that if you randomly made one up, the chances of it being valid would be like 1 in 11, which isn't exactly fantastic. I mean, it's not cryptography fantastic, but in terms of, you know, catching an error that someone made, you know, it's a pretty good chance of, you know, made a mistake. So a library system might have this implemented where you search for a book, it says give me the ISBN, and before it goes off and searches the library, searches the entire catalogue for this number, it would check, well, yeah, does it actually look right? Similarly, with your credit card, I've had to compete with a lot this week now between wasps, rain, and now thunder. Okay. The whole point of this, of course, if we see in the first slide, is that the JavaScript on the client side, on the front end, can check that the thing actually looks okay. Like if you put in a dodgy looking credit card number, well, it's not going to go bother sending it off to the bank and saying, you know, can you authorize this and see if this, you know, transaction can be processed? Because the number itself can't be right. So you don't even bother with that. So it saves a lot of work. Whereas for a phone number, for example, there's no way to know. So if it looks right, you just process it and you have no way of knowing. So it saves you sending off information to the server and processing it when it clearly can't be right. Okay. Can anybody see a problem with this? A mod of anything, the smallest number it could give you is 0, obviously. What's the largest number mod 11 could give you? 10. Mod 11 will never give you 11. It'll give you 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's easy to see if you get 5 what you use here for 5. You know, you just put in 5. But what if it's meant to be 10? There's a problem there then. So as it turns out, ISBN numbers can end with an X. And that X represents 10. because that's 10 in Roman numbers. So the last digit of an ISBN number can be a digit or an X. And if it's an X, it has a value of 10. So you see that that X there multiplied by 1 is 10. So you can get lots of examples of these on Amazon, for example. It's a great place to get ISBN numbers, new and old. Typically on Amazon, it'll list the old ISBN number and the new ISBN number, and Amazon has its own made-up Amazon number as well. Now, so ISBN 10, as we started calling it, that's no longer used for new books. So new books just get the ISBN 13. And actually, ISBN 13 numbers are basically EAN 13s, except the country, we had a special code for Bookland. So they don't come from a specific country, they come from the land of books. And so that's why they all typically start with the same. And so that's just an EAN 13. So if you had EAN 13 code and then you needed some ISBN 13 code, well, you just copy and paste that. It does the same job. It's the same checksum. Okay? So if you go along to Amazon, you can compare these. What's interesting was that when they switched from ISBN 10 to ISBN 13, a lot of people thought, well, okay, I just put then, 978 in front of the ISBN 10 and I'll be sorted. But of course, they didn't understand that you had to recalculate the check digit at the end. Okay. Generally, we have mods in our checksums. When you're looking at checksum algorithms, typically there's a mod in there. And there's a whole sort of science to this, which I won't go into mostly because I don't understand. But you often see prime numbers as well. So prime numbers work very well. So you may see mod 11, for example, mod 23, it's very popular. You might see mod 13, depending. Mod 97 even, I think French ID numbers, is 97 a prime number? If I'm not mistaken, I think French ID numbers do a mod 97, not to be outdone. Okay. Generally, the mod needs to be greater than the range of possible digits. So like if you've got let's say your digits were in hexadecimals, you could go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Then you wouldn't use a mod 13 there because 13 would be less than 16. Generally use something bigger. So you might have a mod 23 or something there. Okay. Now, PPS numbers are ID numbers in Ireland, basically. So all of your interactions with the state involve you using your PPS number. In Ireland, unlike some countries where they're very sloppy with data protection issues, the number of agencies that can ask you for your PPS number is very, very small. So the guards can't even ask you for your PPS number unless they want to give you a job. Okay, it's very highly regulated. So there was a time you got it when you first started work. So when I got my first job or signed on for the first time, I got my PPS number. But nowadays you get it at birth or when you enter the country first if you're coming from abroad. Okay, and it's 7 digits followed by a letter. So all of you have it. Well, some of you don't have a PPS number. If you're an Erasmus student, you don't have a PPS number. But everyone else does, because to be a student, you have to have a PPS number anyway, even if you never had one. So you have your 7 digits and a letter at the end. And you can see this is somewhat inspired by the ISBN one. So the first digit's multiplied by 8, the next one's multiplied by 7, the next one's multiplied by 6, the next one's multiplied by 5, and by 4, and by 3, and by 2. And once again, the check digit doesn't get multiplied by anything, so it stops at 2 there. Okay? So this here is a number I made up. Apologies to whoever owns it. Somebody somewhere owns this. So the 6 there gets multiplied by 8 to give you 48. The 0 gets multiplied by 7 to give you 0. The 5 gets multiplied by 6 to give you 30, and so on all the way down to the 2 getting multiplied by 2 to give 4. So this gives a total of 169. Okay? Now, if you do 169 mod 23, you get 8. So then we have a mapping of letters to numbers, where A is 1, B is 2, C is 3. You could see this wasn't designed by a programmer. The programmer would probably have started at 0 and gone 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, G, and kept going. But anyway, so A is 1, B is 2, C is 3. That can be a pain because everything in JavaScript starts with 0. Like when you have an index into something is usually 0. So even January is month 0 in JavaScript, not month 1. It's that bad. So sometimes you're off by 1 when you're writing your code. But anyway, so we have this mapping of letters to numbers. So if your mod 23 comes out at 8, then your letter should be H. And if the letter isn't H, well then there's an issue. The most likely thing that happened is that somebody transposed the digits. So let's say here, instead of saying 60599, we said 60959. So in this case, the 9 would have been multiplied by 6, and the 5 would have been multiplied by 5, and I was hoping I could work out in my head what difference that would have made to the total, but I realize now that I can't. But the number would be different, so the mod 23 would be different, and it wouldn't come out at 8, it would come out at something else. So that number, whatever it was, wouldn't match up with H. So there'd be something wrong there. A long time ago, women were given their husband's numbers with a W at the end for wife. We don't do that anymore, but that's why sometimes there was an extra space. So this person here, if this person here was my dad's age, then his wife would have been 6059922HW. Because
PPS numbers are 2 letters.
Yes, because you have kids, don't you? No?
Well, it's not me only.
Oh yeah. So we'll come to that, okay? Note there too that W and 0. Obviously, mod 23, the smallest value it can give you is 0. So if A is 1, then what's the letter before A? Well, there isn't one. In this case, it's W. Okay, so 0 gives you W. So you can imagine there's going to have to be a line of code, if thingy equals 0, then thingy whatever equals W. Okay? If you're not careful, otherwise you could end up with the character that comes before uppercase A in the ASCII table, which would be ASCII 64, whatever that is. I don't know. Okay? So don't get caught out there by the 0 and the W. I see people forget that when they're coding this one up. Okay? Now, so if you have 1, 2, 3, 4, 5, 6, 7, A, that only allows for at most 10 million Irish people ever. Now, there's only about 5 million of us at any one time on a good day, about 4 million, 5 million. People in Northern Ireland wouldn't be getting Irish PPS numbers, so it's really even less than 4 million, maybe 4. But of course, we don't reuse the numbers of dead people. So you could probably do some maths about, how many people are born every year in Ireland and figure out when you'd eventually run out of numbers. But eventually, anyway, we would have run out. So from 2013, anyone who got a PPS number got a new one, right? So if you were a baby born in 2013, or you were someone who moved here from Poland in 2013, you got a new number. Okay? And they went to great lengths. I was very impressed actually when I saw the new scheme, because they wanted to preserve compatibility with the old scheme. So it was very well done actually. So now you have two letters. So my son born after 2013 has a 2-letter PPS number. Okay. So you can have 1 or 2 letters now. So have an old number or a new number. Okay. How many million Irish people can we have now? If we could have 10 million before, now we can have 260 million now. So we won't run out for a while. That numbering system might outlast the state. Okay. So once again, we multiply by 8 or by 7, by 6, by 4, by 3, and by 2. Okay? But if there is the extra digit at the end, then that gets converted to a number using A equals 1, B equals 2, C equals 3, so on, blah, 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 blah. Okay? So this A is 1 multiplied by 9 gives 9. So we total all those up then, and in this case it would have been 121. 121 mod 23 equals 6. So 6 is A, B, C, D, E, F. So if you're looking at the code even for the old one and the new one, you know, there's an awful lot in common. And in fact, the way the scheme is designed, code written for the new scheme will automatically work with older numbers. Because if this last letter isn't there, if it's blank, or if it's W in fact, it's got a value of 0. So if the second letter isn't there, then its value is 0. And everything works anyway, like it did before. So new numbers, if you plug them in, so old numbers, if you plug them into the new algorithm, work just fine. Which is pretty handy, because otherwise you'd have to have, you know, if old number, then blah, 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 else, blah, 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 everywhere. Okay? I can see now some are losing the will to live. Okay, another one. So, banknotes. The first letter of a euro banknote actually tells you the country in which it was printed, as it happens. And if you convert that to a number, where A is 1, B is 2, C is 3, D is 4, and then you add up all the digits, you'll get a number. If you add up all those digits and keep going until you've only got one digit left, you should get 8. Which is what this is about. So here are some many made up serial numbers, and then very few of them are real actually. Okay? As it turns out, if you take a serial number, we take this serial number here, X0411 whatever, okay? If you take 041359 blah blah blah, right, and treat that as a very large integer, and you add the 24 to that, and that's a very large integer, it turns out if you do a mod 9 of that, it works out the same as adding up all the digits, which is kind of handy. I think the only circumstance in which it wouldn't work is if it added up to 18. If it all added up to 18, then mod 9 wouldn't give you 9, it would give you 0. But otherwise it should work.
New tenors have 2 letters.
And so do new fivers. So the Europa series of banknotes uses a different checksum calculation. Oh, well, does it? I think the algorithm is very much the same, but I haven't actually, I only saw it for the first time today because I've been Googling it for a long time. I saw it for the first time today. It seems to be pretty much the same algorithm as before, just with a better extra bit of information. So I haven't tested it yet, which is why I haven't told you about it. So the new fivers and new tenors. I was actually looking for old fivers this morning, just to get the serial numbers off them. It's very hard to find old fivers now. So the new ones have 2 letters. I think all that has happened is that the first letter, once again, tells you the country, although the ordering is different. And then the letter A becomes 1, and you add that in. And it just gets added into the total. Again, the main reason for doing that is that now by using a letter instead of a number, you have 26 possibilities instead of 10. So it just means you can keep it shorter. Just have a look at some other ones, just some variations, but they're all variations on a theme really, eventually, once you start seeing more of them. Finland used to have, they used to call their PPS number, whatever that is in Finnish. I think they've changed it since, but the numbering system goes like this. So the first 6 digits are your birthday. But they ran into a bit of a Y2K problem because they were using like day, month, year. So the first 2 digits are the day, next 2 are the month, next 2 are the year. So obviously on your ID card it probably doesn't even say your date of birth because it's obvious from the number you have. And then there's there's a separator. So if you were born in the 1800s, that's a plus. If you were born in the 1900s, that's a minus. And if you were born, if it's just A then, if you were born in the 21st century. So I guess they saved a digit, by doing it that way. Then PPP, the last 3 digits are individual, unique to each person. So I guess they're just issued in sequence. And you get an even number if you're female and an odd number if you're male. Which means actually that only 500 men could be born in Finland on any day before the system would break down. If there were more than 500 men born in any day, you'd have a problem. But the birth rate in Finland isn't really that high. Okay. So looking at Finnish person's number, you could tell whether they're male or female, you could tell their birthday. I'm not sure how they give out the numbers. You might be able to tell whether they were born sort of in the morning or in the afternoon, depending on how low or high their number was. I don't know. The last digit then is the checksum, and this is calculated by treating the numeric part. So you take out the separator. Again, from a programming point of view, you can imagine you have a string. You have to extract the first 6 characters and then ignore the 7th one, the S, and then the next 3 characters. You put those together and you treat that then as a large integer and you do a mod 31. No. Okay. So you do a mod 31 and then that's going to give you a value obviously between 0 and 30. And then this maps to this sequence of characters here So you could have a 0, a 1, a 2, a 3, and we have A, B, C, D, E, F. Notice there's some missing. It doesn't go A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. So it's not straightforward. They've left out some. Why do you think they've left them out? Yes. The wrong obvious answer is that there's no O in finish. But there is. Basically, the letter O looks very like the number 0. Easily confused. The whole point of this scheme is to avoid confusion. The whole point is that you're in a scenario where maybe someone has written it down on a form, you're typing it into the system, and you want to flag it if there's possibly a problem. Having zeros and O's in the same scheme just, causes problems. Obviously, when you see zeros in the first part, you know it's a number. Okay? Because you're used to that being the numeric part. But if you had the letter O at the end, if that was an option, is it an O? Is it a 0? In Ireland, we even talk about O as if it was 0. We say my number is 087 instead of 087. So you can see how that could be a problem. Similarly, I can look very like a 1. What else is missing? A, B, C, D, E, F, G can look very like a C. H, I, like we said, J, K, L, M, N, O, P. Q can look very like an O, an uppercase Q. So you can see they've taken some of them out. Okay. Let's keep going. So I basically want you to go away and code up as many of these as you can find. I definitely want you to do the PPS number, at least the straightforward PPS number, and then modify it to do the big extended PPS number. In some other places, you see in China, for example, it's a mod 11. The UK one uses checksums. Italy is mod 26. You can tell what your mother had for breakfast the day you were born, looking by an Italian person's number. In the US and Canada, they share a numbering system, but the Canadians use a check digit and the Americans don't. Different barcode systems. Your CAO number has a check digit at the end, but no one will tell me how it's calculated. Apparently, it's a state secret. So when I get my security clearance, I'll find out about that one. Okay? So what I'd like you to do now is maybe take out your credit card, pass it around to everyone, and see if you can work out that the check digit is correct. You could also have get out your PPS number, pass that around with the credit card, and see if you can work that out. Okay? On the handout there, I put on the back section of the handout I gave you last week some pieces of code that you'll probably need when you go to code these up. Some various functions there. The index of will tell you, we looked at this already before, but it's worth looking again. So the index of will tell you where the first occurrence of a character is in a string, or a substring is in a string. You can extract pieces of strings using substring. Parseint is very important. We saw this already as well. Parseint converts from a string to an integer. You may need to convert the character 3 to the number 3. Okay? Char at returns the the character at a specific point in a string, and char code at returns the ASCII value of a character in a string. Okay, so the programming of these will be quite interesting. Okay, so I would say start with a credit card. Just today even, I'll turn on the lights now in a second. Your PPS number, see if you can work that out. If you have your bottle of, what is that, 7-Up? There's a barcode on that. Work those out, okay? And just do a couple of them just to see how it works.